All right. So what we're going to be doing today is we're going to be reminded about what the strong acids and strong bases are. Then we're going to talk about what happens in an acid-base reaction. Basically, it's like a ping pong match of a proton, an H plus moving around. Then we're going to look at how you can look at the structure of a molecule and predict, yeah, that's going to be an acid or not. And then finally, we're going to finish by calculating the pH of a strong acid solution. It's a way of measuring the general acidity or basicity of a solution. So as a review, let's talk about the calling cards of acids and bases. So in an aqueous solution, what is it that makes something acidic? What is kind of the calling card of an acidic solution? Well, it's the ability to create H pluses, protons, or hydroniums in an acidic solution. So an example is HCl. So HCl, if it's in water, so we said before, HCl is one of our strong acids. So HCl breaks apart completely in water, just like what happens with our salts like NaCl. Turns out that the products are really stabilized in water. So we end up with H plus and Cl minus. Strong bases, however, their calling card is a hydroxide. So for example, potassium hydroxide, really any group 1 hydroxide. So lithium hydroxide, sodium hydroxide, potassium hydroxide, strontium hydroxide, rubidium hydroxide, and in any group 2 calcium and below. So like calcium hydroxide, strontium hydroxide, or barium hydroxide, etc. So the 7 strong acids, once again, the first 3 are just a proton, a hydrogen, and a halogen. So we have HCl, HBr, and the friendliest of them all, hydroiodic acid. And in the words of the great poet and philosopher John Bon Jovi, whoa, we're 3/7 of the way there. But there are 4 more. So they are H2SO4, sulfuric acid, nitric acid, HNO3, HClO3, and HClO4. And you'll notice that the commonality of these are that they all have a metric crap ton of electronegative atoms and a lot of oxygens. And we'll see how that structure makes them strong in just a hot second. So then recall that strong bases are any group 1 metal hydroxide. So for example, LiOH, NaOH, KOH, etc. And then any group 2 calcium and below. So like calcium hydroxide, strontium hydroxide, etc. Okay, so this is a slide that we've already looked at, but we looked at it last week, so I wanted to revisit it because we'll want to be able to identify the strong acids versus strong bases. And then recall what makes them strong is that when they dissociate, they go all out. So HCl, for example, will turn completely into H plus and Cl minus. Now, technically speaking, 1 out of every billion or so might stay together as HCl, but for the most part, these things are 99.999% going to be ionized. Calcium hydroxide, same situation. It's going to dissociate completely into calcium 2 plus, and it's 2 hydroxides. So when it goes all out. Hydrofluoric acid, on the other hand, HF, not so much. This one, we have to use this equilibrium arrow down here. And what this shows us is that this is more of a wishy-washy reaction. It's not going to go completely to one side. In fact, for every 1,000 HFs, about 1 of them or so is going to dissociate. Okay. Are there any questions about this before we move on? Okay, let us move on then. So usually in class, we use this thing called the ammonia fountain. It's really, really neat. I don't have an ammonia fountain here at home, so we're going to look at a video of an ammonia fountain. So ammonia NH3 is basic, and you'll recall that in order to be basic, something has to create hydroxides in aqueous solution. So we have a bit of a molecular mystery here. And let me pull up the ammonia fountain. Okay. Wait for it. Wait for it. Okay. So let's see what it does. We have this bulb at the top that just has ammonia gas in it. So
we're going to put in a medicine dropper that's sealed with a little bit of grease. The medicine dropper contains a small
let's
amount
watch
of
and see what
water
happens.
and phenolphthalein, which is an acid-base indicator. We're going to lower the tube connected to the round bottom flask into a large beaker of water. We're going to inject the water from the dropper into the flask. The ammonia gas is very soluble in the water and very rapidly dissolves in the water, creating a low pressure situation inside the flask. Atmospheric pressure will force the water up into the flask. We get a fountain.
Woo.
The solution is pink because ammonia dissolved in water is basic and turns the acid-base indicator pink.
So we'll talk more about acid-base indicators at the end of class today. But what that purple is showing us is that the ammonia is creating hydroxide in the solution, which is interesting because NH3 doesn't have an oxygen in it. How can it make OH minus? We have a molecular mystery. Let's solve it. So just FYI, the way that this works, they did a nice job explaining it in that video. Okay, so how does it work? So basically what we have is there's a lot of ammonia, which is NH3, up in this flask. So when a little bit of water is put into that tube, the ammonia is dissolved into the water. Let's draw some incredibly realistic water here. When that dissolves, it lowers the pressure that's in the tube. So then the lower pressure creates this almost like vacuum situation that pulls more and more water up into our tube. So the water goes up into the tube. As more water goes up, more ammonia dissolves. And then everything turns purple because ammonia is a base, it reacts with the water and ends up making hydroxide. So how is it that ammonia does that? What is it about ammonia that lets it create hydroxide? So the idea is that the ammonia actually reacts with water. It forms this thing called ammonium, NH4+, and it leaves behind hydroxide, OH-. So we need a different definition to talk about acids and bases, because before we just said, oh, an acid leaves hydrogen in an aqueous solution, or a base leaves hydroxide in an aqueous solution. It's not always as simple as that. Well, I hope you'll see that these definitions work together nicely, but we have to invoke this thing called the Bronsted-Lowry definition. And the acid definition works pretty well. The acid definition is if it's in a solution, it will donate an H+ for an acid, which is what we know about acids. Acids, H+, that's their calling card. Where this is different is the definition for a base. Bases, it turns out, does the opposite. They do the opposite of acids. So whereas acids get rid of H+, bases will gladly accept H+. So we have that definition down here. So the acid will say, take this, I don't want it. The base will say, okay. So in this particular reaction that we have here, NH3 is acting as a base because it's grabbing a hydrogen from water. So that means that the water here is acting actually as an acid. So the water is getting rid of its hydrogen, and the base is gladly taking that hydrogen. And then in the end, that creates this hydroxide over here, which again is kind of our calling card of basic solutions. Hydroxide, classic. So what we have is, even though this molecule doesn't have hydroxide in it, it's still able to react with water to make hydroxide. Classic base maneuver there. That's what bases do. That's how they roll. Does anybody have any questions about this reaction that's happening here? And as always, please feel free to either unmute yourself, use a microphone to ask, or you can ask it to the chat. So ammonia is a base. And what's happening in this reaction is, we're going to see that whenever you have an acid-base reaction, there's always going to be both an acid and a base. One thing is going to get rid of an H+, and one thing is going to gain an H+. So that's actually a perfect segue question onto our next slide. So what is it about ammonia that makes it react with water? So what do we know about the nitrogen in terms of hydrogen? Which one's more electronegative, nitrogen or hydrogen? Good, the nitrogen. So nitrogen basically hoards electron density. We get this really, really negative charge on this nitrogen. Meanwhile, on the water, the hydrogen has a partial positive charge. So what do we know about negative charges and positive charges? They attract each other. So the nitrogen's like, woo, a positive proton. And basically, it goes yoink, and it ends up grabbing onto that proton. I like to think of these reactions as almost being like one of those crane games that, you know, one of every 3,000 times you can win, but like it goes and actually that's kind of appropriate, because it's about 1 out of every 1,000 times that ammonia will actually succeed in getting that proton, but it does it enough to create the hydroxides. So we actually get what's called a nucleophilic attack. And this stuff, we're not going to be doing any electron pushing in our course, but I just think it's kind of useful for visualizing what's going on here. Those electrons actually physically create a new bond. Hydrogen, though, hydrogen can't take more than 2 electrons, so it can't have 2 bonds, which means that something's got to give, and the other electrons on hydrogen basically retreat back onto the oxygen. So this is just kind of a visual schematic of what happens with this reaction. Okay? Again, we're not going to be doing electron pushing, but for those visual people out there, this is what actually happens at the molecular level. So now we're going to go into this idea of acids, bases, conjugate acids, and conjugate bases. And it's a really important relationship in acid-base chemistry. So we have our acid. It has a proton on it. When it dissociates, when it gets rid of its proton, it becomes a conjugate base. So I have here a generic reaction written out. We have HA, some generic acid, reacting with B, a generic base. The proton gets lost by the acid and scooped up by our base. So the products of this reaction, we have A minus because our acid got rid of one of its positive charges. It got rid of an H plus, so now it's got a negative charge. And our base now has this newly found H plus on it, so our base has a positive charge. So in this reaction, generic acid HA is our acid. And just so you know, as a convention, oftentimes acids are written with H in front because it's the H that makes them an acid. B is our base. Whatever the acid becomes after it loses its hydrogen is what's called a conjugate base. So our acid starts off with its proton, it gets rid of it, and the thing that it becomes is known as a conjugate base. Whereas the base, after it gains a proton, becomes known as a conjugate acid. So that's kind of a generic look. Let's take a look now at two different reactions. One where we just have the chemicals spelled out, and then one where we actually have the molecules drawn out to identify what's the acid and base in each reaction. So in the second reaction down here, we have our hydrogen on HCl, and then we have this molecule over here, which is called carbonate CO3 2-. So we can see here that in our products, the HCl got rid of its H+ and just became Cl-. So whatever's getting rid of the hydrogen on the left-hand side of the reaction, that's our acid. Whatever is accepting that hydrogen is the base. So the HCl is the acid, the carbonate is the base. The base, once it gets that proton, becomes known as the conjugate acid. And the reason why it's called a conjugate acid is because now it has that H+ that it could theoretically then donate to something else. And the acid, after it loses its proton, becomes known as the conjugate base. Okay, so this next one, the question is, what is the acid and what is the conjugate acid in this reaction here? So take a moment. In order to answer this question, write out the role of everything. So write out what the acid is, write out what the base is, write out what the conjugate acid is, write out what the conjugate base is, and we will have a poll to answer it. And that poll is elegantly worded, which answer is correct. So take a moment. And once you have your answer in, once most people have answered, we will continue. Right, we'll give this another 15 seconds or so. Okay, and we'll close this poll up. All right, and so the answer is D. Well done. So if we go through and we look at the roles of everything on this reaction, our hydrogen is right here. The hydrogen from water is lost, so that makes water the acid. The nitrogen is what gains that proton, that H+. So whatever gains the hydrogen is known as the conjugate acid. Whatever the molecule becomes, whatever the acid becomes after it loses its proton is known as the conjugate base. Nice job, y'all. Are there questions about this? Okay. So just a quick little gauntlet to practice coming up with a conjugate acid and conjugate base. If you ever have to find the conjugate base of something, all you have to do is remove an H+ from it. So for example, HCl. Its conjugate base is just Cl-. Whenever something loses an H+, its charge goes down. So that's why HCl, after it loses the H+, becomes Cl-. H3O+, if it loses a proton, well, it's the same molecule, except without an H+, so now it's just H2O neutral. In order to figure out what the conjugate acid of something is, all you have to do is glue an H plus to it. So we have hydroxide as our base. What's the conjugate acid? All we're going to do is plop a hydrogen onto it, an H plus, and we get H2O. So a few more examples, NH4 plus. Yeah, that's a great way of thinking about it. Acids and conjugate bases basically have inverse relationships to each other. I really like that. It's an excellent way of thinking about it. So NH4 plus, if we want to find the conjugate base, we take a proton away. Down here, we have a molecule called bisulfate. If we add a proton to it, we get its conjugate acid, H2SO4. If instead we took a proton away, we'd get the conjugate base, which is SO4 2-, molecule called sulfate. And we'll talk a little bit about the relative strength of acids and bases in just a hot second. But generally speaking, the stronger an acid is, the more it wants to get rid of its H plus, the weaker the base is that it creates. And we'll see why that is in just a moment. So now let's talk about why something will act as an acid and why some things maybe not so much. So this molecule right here is an old friend of ours, carboxylic acid. And carboxylic acids, appropriately enough, are acids. Over here we have an alcohol. This molecule, not really an acid. Why is it that one will get rid of a proton, whereas the other one will not? That is the question we seek to answer here, how the structure affects the function. So let's get to it. What is it about the carboxylic acids OH that makes it so much easier to break? It turns out it has to do with the bond polarity. So if we imagine our oxygen and our hydrogen and the electrons, which atom are the electrons more attracted to? The oxygen or the hydrogen? Which way are these electrons going to flock in this bond? Which one is the more electronegative, more electron-hungry atom here? The oxygen. Oxygen really, really, really greedy when it comes to electrons. So this oxygen is going to pull the electron density away from the hydrogen. Okay? But wait, there's more. Because downstream, there's another oxygen right over here. So it turns out that even though that oxygen is not directly attached, it still makes a difference in this molecule. So it pulls electron density toward itself and actually has this downstream effect where the electrons are pulled even further away from the hydrogen. So hydrogen, H plus, is attracted to electrons. If we pull the electrons away from it, is it going to be as attracted? Going back to an example we used earlier on in the course, if you have two magnets close to each other, they'll be attracted to each other. The further you pull them away, the less attraction there is. So as a result, well, that hydrogen is not going to be nearly as attracted. So the more we pull electrons away from the hydrogen, the more of a chance there is that it's going to be lost. So this molecule here, the alcohol, it has a polarized bond, but it's not quite tricked out enough to have it be very acidic. Slightly, but not really acidic. So our key idea here is the more polarized the bond is, the more we can pull electrons away from that hydrogen, the stronger the acid becomes. And I think you'll see there is a really quick little rule of thumb that we can use if we evaluate carboxylic acids. So I like to call this tricking out our carboxylic acid, a segment. How can we make a stronger acid? Add more electronegative atoms. So for example, I could put a chlorine on here and make this is called chloroacetic acid. That's going to be a stronger acid than just acetic acid because it's got this chlorine here. So how can we make it even stronger? What is more electronegative than chlorine? There's two good answers here. Three, sort of. Nitrogen's kind of tied. What is the, yeah, awesome, fluorine. Fluorine is the granddaddy of electronegativity. So if instead we put a fluorine there, now we have an even stronger acid because this fluorine, even though it's downstream of the OH, is going to influence that bond. So this will be a stronger acid than the one with chlorine. What would add more electronegativity than one fluorine? How can we make it even stronger? What would contribute more of an electronegativity imbalance than one fluorine? There we go. What if instead we had not one, but two fluorines? Whoa, things are getting pretty crazy here. That would be even stronger. And so on and so forth. If you add a third fluorine, well, forget about it. You've got yourself a really strong acid there. Yes, yep. So the idea is the more we can pull electrons away from that hydrogen, the stronger the acid, because the more we pull the electrons away, the less attracted that hydrogen is going to be. 1, 2, 3 fluorines. All right. So with that rule in mind, we're going to do another clicker question. Okay. So these are 4 different acids. We have hypochlorous acid, we have chlorous acid, we have chloric acid, and we have perchloric acid. Given these, which of these acids do you think would be the strongest? And you don't need to know the names of these. I'm just going to write out our answer choices there. To the poll! Okay. Our poll is open for business. Which of these is the strongest acid? And we're going to give this another 20 seconds or so, but think about that rule that we said on the previous page. Okie dokie, please get your answers in 5, 4, 3, 2, 1, and 0. And I like what I see here. The answer is indeed A, HClO4. So a rule that will always work for our purposes is the more electronegative atoms, like chlorines, oxygens, fluorines, that we put in our acid, the stronger it's going to be. Nice job. So let's look at a really, really high-tech simulation of what happens here. So we have HClO, which is a weak acid. Case 1, the weak oxy acid. So the reason why this is an acid is because we've got this oxygen here, and the oxygens are like, yoo-hoo, electrons, I'm really electronegative. And the chlorine is like, yo, electrons, I'm pretty electronegative too. So those electrons, they move more toward the oxygen and chlorine. Now that they're moving further away from the hydrogen's all like, well, shucks, I'm not as attracted now that the electrons are being pulled away. Perhaps I will dissociate. And so this bond is more polarized and weaker. Ooh, and it can break. But can we make this stronger? Yes, we can, because as you pointed out, HClO4 is a stronger acid. In fact, it's so strong it's called a strong oxy acid. So what happens here? Yoo-hoo, electrons, yoo-hoo, 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 yoo-hoo. There's so many electronegative atoms here. What's going to happen? These electrons, they're really going to be attracted. Now, whoop, they're moving so far away from that hydrogen. And the oxygen's all like, how are you doing? And the electrons are all like, better now, bae. This is actually what they say to each other. I don't know, it's just science. And because the electrons are really far away, the hydrogen, not attracted anymore. The electrons that was gluing it to the oxygen, they're far away now. So that's it, it's out of here. And then it just goes. And for some reason, in an Adele reference, it then says goodbye from the other side. Again, I don't know why that is, it's just science. So here we have our general trend. More electronegative atoms makes for a stronger acid. And the more of those electronegative atoms that you have, the stronger the acid is going to be. So with that in mind, take a moment and rank these carboxylic acids from the weakest to the strongest using those rules that we just discussed. So take a few moments and we're going to go to Pole City, population, everybody. I'll cue the polling music.
We're going from least to greatest, right?
Yes. Yep. So we want the weakest first and then the strongest last. Please get your answers in if you haven't already. In 3, 2, and 1. And awesome work. The answer is indeed C. Excellent. And again, that rule of thumb that we can use, the more electronegative atoms you have, the stronger the acid is going to be. And so if we look at these possibilities, the weakest one only has hydrogens other than the carboxylic acid functional group here. So hydrogen's not really electronegative. Number 2, in terms of strength, has 2 chlorines. Okay, that's pretty electronegative, but more so would be 2 fluorines. But wait, what's more electronegative than just 2 fluorines? Having 3 fluorines. So that's the reason why we get that particular order. Very, very good job. So now let's talk about what it means for something to be a strong acid versus a weak acid. The idea is that if you have enough of a polarized bond, that bond is going to break and those hydrogens are going to be donezo with the molecule. So strong acids dissociate completely in the forward direction. Once that bond breaks, that hydrogen's gone. Weak acids, on the other hand, they just dissociate partially. So weak acids use our equilibrium arrow because the idea is, so weak acids use an equilibrium arrow, strong acids use a full-headed arrow. Strong acids, when they go all out. They break apart completely. Weak acids, they're a little bit more wishy-washy. Like some of them will break apart, but even once that hydrogen's lost, sometimes it comes back again. You can have both the forward and the reverse reaction happening. And then finally, the other category that we have is something called a negligible acid. These are too weak to even be called weak. These ones are holding on to those protons. They're not going to give them up. They're not going to let them down. They're never going to say goodbye and desert them, okay? Those ones are holding onto the protons, none of the protons are going to leave. So these are our three different levels, we'll say, of acids: strong, weak, and negligible.
So quick
Sometimes
question.
Yeah.
So when we have weaker acids or base, so let's say you have a solution of an acid or in a base. So does that mean that the reaction continues to flip-flop?
It does. It eventually
or does it eventually find a middle ground?
It finds a middle ground. So it finds a ratio of products to reactants, something called the equilibrium. The reaction actually still happens though. So there's still protons being exchanged and whatnot. It's just the relative level of the products to the reactants stays consistent. So the reaction is still going, but there is no net change.
Okay.
It's like if you have a glass of ice water at the freezing point of water, like perfectly at the freezing point. Some of the ice will be turning into liquid water. Some of the liquid water will be turning into ice, but there would be no net change. It's going to stay like kind of perfectly at the ratio that it's at.
Okay, thank you.
You're welcome. Very good question. So here we have a whole table. Looks kind of imposing here. But basically the idea that you want to take away from it is, at the top you see, hi, HBr, HCl, H2SO4, HNO3, HClO4, HClO3. What are the commonalities of all those? They're all strong acids. So they all have this full-headed arrow here, because in aqueous solution, they're going to completely turn in to H+. And just note, the H pluses, saying H plus and H3O plus are equivalent to each other, because technically the H pluses don't just hang out on their own. They bounce around, they bop around from different waters. So you can use H3O plus or H plus, they're equivalent. So strong acids dissociate completely. And once they're broken apart, they never come back. Whereas negligible acids, on the flip side, so if we look down at the bottom here, things like OH minus, H2, CH4, they're not going to get rid of their hydrogens. If a hydrogen happened to be broken off of one of them, it's going to basically instantly go back. So we see here that all of these arrows are in the reverse direction. So if there's a chemical mishap and one of them happens to lose a hydrogen, within instants, it's going to grab its hydrogen back. And then in the middle, we have this whole plethora of things that go through this like ping pong match. The hydrogen bounces back and forth and back and forth and back and forth. So this brings me to one of my favorite rules in chemistry that I'm going to subject you to, and you'll see why I said subject in just a moment. So the conjugate of a strong acid is a negligible base. Once that acid breaks apart, whatever it turns into isn't going to be able to get a proton back. The conjugate of a strong base is a negligible acid. So these things, once they react, they make their products and they're done. So is there some sort of rule that we can use to remember this? There is, and I like to call it the Taylor-Swift hypothesis. So not a lot of people know that in addition to being the songbird of a generation, this is a really awkward setup because I have an armchair here. But in addition to being the songbird of a generation, Taylor Swift, also a chemist. In fact, some of her best known ballads are about acid-based chemistry. And I warn you, this one's a little sad, but we'll get through it. It's Friday, after all. One of her best known songs, some people think it's about John Mayer. It's not. It's about HCl. And what happens is the HCl dissociates, and once that proton's gone, it's all like, we are never, never, never getting back together. We are never, never, never Magic. I thank you. I thank you. The hydrogen's like, we are never, ever, ever getting back together. Chloride's like, I have an indie record that's so much cooler than yours. And the hydrogen responds, like, ever. So once the strong things split, they are donezo. That's it for them. They're gone, the bond's broken, never coming back. That's what makes them strong. I thank you. I thank you. And that's actually the reason why I wanted to do this slide, was just because I wanted to subject you to a little rendition of T Swift. The negligible acids, they're all like, never going to give you up, never going to let you down. They don't get rid of their protons. And another pop culture reference that I could make if I had my capo, but I lent it to a friend and now I can't get it back. Hot and cold. With the weak acids and the weak bases, they're hot and they're cold. They're yes and they're no. The protons, they're bouncing around. They're not really staying with one or the other. Which brings us to our last topic of the day, the pH scale. So in a solution, acid concentration can range from, well, basically most solutions have acid concentrations that range, if they're really, really high concentrations of acid, it can be up to 18 molar. On the low end, they can be 0.0000000000000000001 molar. So there's this long range, and it becomes inconvenient to say, oh, well, the proton concentration is 0.0000. So instead, we use a logarithmic scale, something to help make more user-friendly numbers. And that is called the pH scale. So the way that the pH scale works is you take the negative log base 10 of the H plus concentration. So if we have a strong acid, it dissociates completely. So whatever the concentration of that strong acid is, like if you have 1 molar HCl, that entire 1 molar is going to break apart into H plus and Cl minus. So whatever the initial concentration of acid is, that's going to be the H plus concentration. So if we wanted to put a pH on that, let's just take, for example, a 0.05 molar solution of HNO3. HNO3 is a strong acid, so all of it is going to dissociate into H plus. So that means that we would have a concentration of 0.05 molar H plus. So then what we would do is plug that into a calculator. We would take the log base 10 of that 0.05, and then we would take whatever that answer is, we would make it negative. And in this case, it ends up being 1.30. 1.30 is really, really, really acidic. To give you a baseline, the pH of the stomach, which is really concentrated in acid, is a baseline, is between 1 and 2 in terms of pH. So anything that's less than 2, you're looking at a really acidic solution. And here's just a whole bunch of everyday things and their relative pH levels. So drain cleaner is actually potassium hydroxide. You pour it into the drain, it reacts with clogs vigorously. It builds up pressure from gases, and it helps to both eat away at the clog, but also to help push it and to help melt it. It's a very exothermic reaction. All sorts of things happen. Bleach, also very basic. Then as we move up, we get to blood is slightly on the basic side. The barometer that we use is pure water has a pH of 7. So anything less than 7 is acidic. Anything greater than 7 is basic. Blood is slightly basic. And there's a whole bunch of important reasons why it is that way, but anyway. Then as we go up, peanut butter. Did you know peanut butter was slightly acidic? It is. Black coffee, it's a personal favorite of mine, slightly acidic. In fact, after you drink coffee, it's oftentimes good to brush one's teeth or have a glass of water because it's acidic. And the more acid you have, the more it can eat away at your teeth. Cola, or pop, if you will, has a pH of 2.5. That's really acidic. Also something where if you drink soda, you should have water afterwards to help kind of make sure it doesn't eat away at your teeth. I mean, it's not like it eats away really, really quickly. It's just if you, frequently enjoy soda, just be aware, it's acidic. And battery acid is sulfuric acid. It's super duper acidic with a pH of 1. And there's lots of different ways that we can measure them. A pH meter is the most accurate. You plop it in after you do some calibrating, and it tells you the precise pH of your solution. Another common thing are dyes and litmus paper. Those more rely on an eyeball test. And what you can do is, for example, with litmus paper, if you dip it into a solution and it turns bright red, that means it's really acidic. If it turns bright purple, that means it's basic. If it turns green or yellow or blue, that means it's kind of in the middle. So these are just some ways that we can actually